And then you subtract out this area that I'm shading in green. So you'd just be left with this piece. So if we do that for each one of these polar rectangles, we're going to get the following. We'll get 1/2, and then we're going to get a difference of radii, and we're going to square both of them. Ri squared minus Ri minus 1 squared times the angle that the sector is sweeping across, and that would be delta theta. Okay. So now we can write down an approximate volume of the solid. Here we have several radii between A and B, but here we also have several thetas between alpha and beta. So we have to account for all of these polar rectangles, and we have m times n polar rectangles to consider. So the volume is roughly the sum, a double sum actually, over all n times m polar rectangles. The height is given by the function evaluated at an r and a theta chosen from each rectangle times the area of the polar rectangle at the base. So that would be 1/2 Ri squared minus Ri minus 1 squared times delta theta, where if we have a single polar rectangle, any one of these, so here we have, for instance, R4, R5, defining these R values, and then we have, say, theta 9 and theta 10, doesn't really matter. Then we choose any point within this polar rectangle. So this would be a point R5 star, theta 10 star. So Ri star is any point between these two. We can choose one of these two if you want. You'll get the same result. And theta I star is chosen the same way. So this is no different than how we defined double integrals in x and y. Okay. So now we have a volume, the sum of volumes of relatively simple solids where the height is constant for each one. But now we want the exact volume. So we're going to let the number of polar rectangles go to infinity. We're going to let delta r and delta theta go to 0 and get an integral like we have in previous cases. But in order to get an integral, we need to rewrite this, because in its present form it's not something we can really work with. We can do, if you look at 1/2 Ri squared minus Ri minus 1 squared, algebraically, what can we do with this?
Difference of two squares, right?
Yeah, difference of two squares. So you can split it up. So we have 1/2 Ri minus 1 plus Ri. And then we have Ri minus 1. So what we get here, we get the average of these two values if we include the 1/2. So I'll just put all those together just to emphasize it's an average over here. And then what's this? Well, this is delta r. So now our approximate volume is the sum over all polar rectangles. So we have our function and then we have Ri minus 1 plus Ri over 2. And then we have delta r, delta theta. So now, as we let the number of polar rectangles go to infinity, what we get is the exact volume. an integral from alpha to beta in the theta variable, from a to b in the r variable. We have f of r theta. Now this factor right here, ri and ri minus 1 and ri, those are converging to each other because the widths of all these intervals, these subintervals, are going to 0. So if this converges to r, then we have dr d theta. So this is how we compute the volume of a solid expressed in polar coordinates whose height is given by this function. So one thing you have to be careful about, it's a common mistake, is when you do an integral in polar coordinates, when you're converting from xy to r theta, don't forget the r. There's an extra factor of r that sneaks in there. And it's because of how you compute the area of a polar rectangle. It's r dr d theta. As you notice, if you look at polar rectangles corresponding to the same angle, as r increases, the area of a polar rectangle increases a little bit. So that's why that factor of r needs to be there. Regular double integral, function of x and y, over a region that's also described in terms of x and y. And you have to decide, do you want to do it the way it is, or would it be more convenient to convert to polar coordinates and then compute it? So, find a region D in terms of x and y, where we have x squared plus y squared is less, greater or equal to 1, less than or equal to 4. And then we also have x is less than or equal to 0. So let's draw what that region looks like. So we're going to have circle radius 1, circle radius 2. So this inequality defines the area in between, but x is less than or equal to 0, so we just take this portion right here. Okay. So you can try defining this region. We define it in terms of x and y, but certain regions, especially those that have a circular component to them, may be more convenient to define using polar coordinates. So how would we describe this region in terms of inequalities for r and theta instead of x and y?
We could have an outer bound and then an inner bound. That's the best way I can describe what I've learned, but
Yeah.
being dropped in class, but
Well, that's fine.
you could have a one and then you could just subtract the other from it, like the examples before, right?
Yeah. Well, so what will be bound? Yeah. So we have these two concentric circles here that define boundaries in terms of r. So we want to define inequalities for r and theta. So what is r bounded by for a shaded region? Not 1 and 4.
Square root.
1 and 2.
1 and 2. That takes square root of each. Yeah. So r between 1 and 2. Okay. What about theta? What angles are we talking about here? Yeah, pi over 2 and 3 pi over 2. So the definition of this region in polar coordinates is much simpler than what we had in x and y, because we're dealing with a polar rectangle. So now we can have an integral, the double integral with constant limits in both variables. So let's suppose that our function xy, our integrand that we had in our original integral, is just x plus y. And now we go to polar coordinates. So we'll integrate from pi over 2 to 3 pi over 2 in theta, and then from 1 to 2 in r. And you can order it any way you like, but especially in this case. So we need to convert our integrand to polar coordinates. So what's x plus y going to be?